Hello everyone. Now in these lectures we are going to start the first chapter of class 12, relation and function. So in these sessions we are going to learn what is the relations and domain and range of the relations, different types of relations, and we will do some questions on it. Okay na? So now first part is what is relation. In class 11 you already learn about the order pair. We know that if we have order pair which is belongs to A cross B, it means that A is the element of A and B, small b, is the element of B. So what is relation? Relation is a subset of A cross B. A relation is a subset of all A cross B. That means you can define a relation in this way. Relation is equal to set of all order pair AB such that A is the element of A and B is the element of B. Okay now. So take one example so that what is relation we can understand. Suppose a set A has the elements 1, 2, 3 and set B has the element A, B and C. So if you take their cross product A cross B, you will get what? Total 3 cross 3, that means total 9 elements will come, and these elements will be what? 1 comma A, like this. You have all the 1 comma A, 2 comma A. In this way last pair will be 3 comma C. So there will be 9 elements. If you want to write, you can write all the 9 elements and you can take few of them like 1 comma A, 1 comma B, then 1 comma C, then you have 2 comma A, 2 comma B, 2 comma C. Then you have 3 comma A, 3 comma B and 3 comma C. So from this order pair, set of order pair, you choose some elements from here. So suppose I am taking this one first, then this one second and this one third element. So from these collections of order pair, I am taking 1 comma A, 3 comma A and 2 comma C. So this is my relations. So when you define the relations, you can also write in this way. The 1 comma A belongs to the set R. 1 comma A belongs to the set R, which is same as you can write as 1 is related to A by the relations R. So from the all the cross product A cross B, if you choose any one from here, 1, 2, 3, whatever it is present, if you choose any elements from this A cross B, this will form a relation. So suppose if I take a element which is not present here, 3 comma D, so you can write as 3 comma D is not the element of A cross B, so 3 comma D does not belongs to R, or you can write in this way, 3 is not related to D by the relations R. So this is the basic definition of relations. So when we define the relation from the set A to the set B, so it is what? It is the total R is the subset of A cross B. So if I want to calculate how many relations exist from A to B, it will depends on how many subset we can form from this given set. How many subset we can form from the given set A cross B. So you know that if a set, suppose I have a set X and this set contains n elements, so total number of subset will be 2 power n. So in your A cross B, how many elements are there? That is 9 elements. So total number of relations that I can define, total number of relations from A to B, total number of relations from A to B will be 2 to the power 9. Okay. So 2 to the power 9. From 9, where we get this 9? These 9 elements are present in A cross B. So in A cross B, how many elements present? That will be 2 to the power, that will be the total number of relations. So if I say a set A has m element and a set B has n elements, then we can say that total number of relations from A to B, total number of relations should be 2 to the power mn. I hope this part is clear to everyone. So take one example. Before defining the relation on a set, now try to solve one questions on the based of this concept. Suppose A is equal to containing the element -1, 0 and 1, where B is the set which contains the elements A and B. If I ask you how many relations we can define from A to B, okay now, how many relations we can define from A to B, how many relations? So from A to B, how many relations we can define? It will be total number of relation is equal to 2 to the power m into n, number of elements in A multiply with number of elements in B. So number of elements present in A is 3, number of element present in B is 2, so 2 to the power 5, and it is 32. So total we can define 32 relations from the set A to the set B. Hope you understand this part. Now we define the relations is a subset of A cross B if the relation defined from A to B. So if I substitute this B by A, that means both are the same set, then this relation is called relation on a set A. That means R, if you take A cross A, then it is called relation on the set A. So if I have A is equal to suppose 1 and 2, then you can say that R will be the subset of 1, 2 cross 1, 2. So from here you have to select the elements. Okay now. Now coming to the next part, domain and range of a relations. So for example, if I take A is equal to 1, 2 and 3, and here I am taking the another set, suppose B set, which is equal to suppose alpha and beta. So I define the relation R which is equal to 1 comma alpha and 2 comma beta, or you can say that 2 comma alpha also. So this is the relation which I defined. Now what is the domain of the relation? In the relation, the set of all first element. In the relation, in the order pair, the collection of all the first component is called the domain. So domain of the relation R, will be the set of all first component, that is 1 and 2. If I ask you what is the range of this relation R, so it is the set of all second component of your relation, that is alpha. So this is the domain, this is the range of the given relations. So you can generalize your definition. Suppose you can write in this way: domain is equal to, domain of the relation R is equal to set of all first component X such that X comma Y belonging to your relation, and range of the relation R is the set of all second component Y such that X comma Y belonging to the relation. So from the relation we can only take those elements which are present in relation. So set of all first component is the domain, set of all second component or the collection of the second components is the range of the relations. Okay. Now inverse relation. What is the inverse relations? If you take a relation like R, and its inverse is denoted by R inverse, which is defined as set of all order pair B comma A such that A comma B belongs to the relation. For example, R is the given relation. Suppose R is a given relation. So that means if I have a relation R which is equal to suppose 1 comma 1 square, that is 1, 2 comma 2 square is 4, and 3 comma 3 square is 9. This type of relation I have. So R inverse, you just change the order of the order pair. This will be your just changing the order. The first element will become the second element will become the first element. 1 comma 1, then 4 comma 2, and then 9 comma 3. Okay now. Acha, what you observe in case of, if you are going to find the domain of the relation R inverse, which is equal to the set of all first component 1, 4 and 9. 1, 4 and 9. So you notice that 1, 4 and 9 is the range of the relations R, which is equal to range of the relation R. Next is range. Range of R inverse, which is the set of all second elements. So that is 1, 2, 3. And 1, 2, 3 are the first element of the relations R. So that is the domain of the relation R. I hope this part is clear to everyone. What is the relation between the domain and range of the R and R inverse? So its domain is nothing but the range of R, and its range is nothing but the domain of the R. So that will be interchange. Domain becomes a range and range becomes a domain for the R inverse. Now next is different type of relations. So first is empty relations. Since phi is a subset of every set, we can write phi is a subset of every set. So therefore we can say that phi is also a relation, because the definition of relation is the subset of A cross B. So if you take the relation on the set A, then phi is a subset of every set. So phi is the empty relations. Take one example to understand what is the empty relation. Suppose if I have a set A which has the element 1, 2, 3 and set B has the element 4 and 5. So here if you add the order pair, so 1, 4 is the minimum, 5 and 5 plus 3 is the 8. Now I am defining a relation R such that, which is the order pair of XY, such that X plus Y will be 10, where X belonging to A and Y belonging to B. So you have to take X from A. So maximum you can take 3. If you choose Y, maximum it will be 5. When you add them, it will be 8, but it never be 10. So you cannot find any order pair from the A cross B which will gives you 10. So therefore R is the what type of set? Null set. So it is called empty relations. I hope this part is clear to everyone. Now universal relation. Universal relation is what? We know that if I say A cross A, if you take all the order pair, then the relation that you defined, it is called the universal relation. In the previous example, what I am taking, the 1, 2, 3, 4, 5, the addition is maximum 8 and minimum is 5. So if I choose my relation R is set of all X, Y such that 5 lesser than equal to X plus Y and lesser than equal to 8, where X belonging to the first set, Y belonging to the second set. So what you observe that every order pair of A cross A will be in the R. That's why R is called the universal set. Okay, now coming to the next part, identity relation on the set A. So if you take any set A, the identity relation is defined as I of A, which is equal to set of all X, X, where X is the element of A. For example, if you take A is equal to 1, 2 and 3, so I of A will be the element which is associated with itself, is called the identity relations. So that is 1, 1, 2, 2 and 3, 3. This is nothing but the identity relations. Okay, now I hope this part is all of you, this part is clear to all. Now coming to the reflexive relation. So if we have a set A which is non-empty set, throughout my lectures when I define the relations, you should assume that A must be the non-empty set. Okay, now from the beginning. I assume that all of you know about the relation from the class 11. That's why I'm not writing here. A is not equal to 5 and we defined a relation R on A. So a relation is called the reflexive relation. A relation R is called reflexive relations if A, A belongs to R for all A belongs to capital A. What does it mean? Suppose if I have A is equal to 1, 2 and 3, so you know that total 9 order pair I can define. A cross A contains total 9 order pair. So this order pair I am going to write in the matrix form. It will help us to do some more problem here. So this will be 1, 1 order pair, 1, 2, 1, 3, then 2, 1, 2, 2 and 2, 3. Then 3, 1, 3, 2 and 3, 3. Okay, now so reflexive relation is what? A relation if you defined where every A is associated with A. So that means if you can take here relations R1 like in this way, R1. So if you take 1, 1, 2, 2 and not any other element, 3, 3 if you left. Now if I ask you, is this the relation? Is this the relation? A reflexive relation? Answer is no. It is not reflexive relations because A contains 3. A contains 3, but 3, 3 is not present in your relation. So it is not a reflexive relation. Now the second question, R2, if I write 1, 1, 2, 2 and 3, 3, is it reflexive relation? Answer is yes. It is reflexive relations because all the elements is associated with itself. 1 is associated here, 2 is associated here and 3 is associated here. Now if I defined here R3, if I ask you R3 is reflexive or not, where R3 is 1, 1, 2, 2 and 3, 3 and any other pair I am taking from these collections. Suppose from here I am taking 3, 1. Now my question is this one is the R3 is reflexive or not. So for reflexive the condition is what? The condition is A, A belonging to R for all A belongs to A. For all A belongs to A. So here in the set A 1, 2, 3 belonging. So therefore 1, 1, 2, 2, 3, 3 is present. So this is sufficient to satisfy this definition. Whatever the extra element will come, it will not affect our definitions. So therefore it is also a reflexive relation. So this is the difference between what you observe, that this is the difference between the identity relations and a reflexive relation. In reflexive relations, A, except A, for all A belongs to A, other order pair may present. Other orders pair may present, but in this relation, identity relations, only the diagonal elements 1, 1, 2, 2, 3, 3 only present. No other elements will allow. So you can say that this relation R2 relations, which is reflexive, is also identity relation. So what do you observe? Every identity relation is a reflexive relation. Every identity relation is a reflexive relation, but every reflexive relation is not the identity relations. So identity relations on some set A implies it is the reflexive relation, but reflexive relations does not always implies identity relation on the set A. So every identity relation is the reflexive relations, but every reflexive relation is not the identity relation. Now the question is, if I have a set A, if I ask you how many identity relation you can define, so only one identity relation you can define on the set. That means you have to choose all the diagonal elements. But what about the reflexive relations? If I ask you, if the set is given, then how many reflexive relations you can define? So first of all, this part is compulsory. You have to take all these elements. There is no choice. So for every diagonal elements, you have only one options you have to choose in your set. Now what about the remaining elements? What about the remaining elements? So here, if the matrices, if you consider here nth order matrices, so diagonal has only n elements. Here you notice that total 9 elements. So 3 cross 3, 3 by 3 is the order of the matrices. Total elements is 3 into 3. Now non-diagonal elements is what? For the non-diagonal elements, you just subtract this one. Number of elements in the diagonal element is 3. So what we have? 3 into 3, 9. 9 minus 3, that is 6. So for the remaining elements, you have the total 6 choices. So now we are going to calculate the how many reflexive relations we can define on the set A. So what I said that this element is compulsory to define the reflexive relations, and for the non-diagonal elements we have, for every element we have the 2 choices. So now we can write total number of reflexive relations will be For the diagonal elements, there is no other choice you have to take, that is the one choice for every elements. So 1 power 3. And for non-diagonal elements, we have two choices, either you can take or you can reject. So 2 to the power n square minus n. So this will be the formula for total number of reflexive relations. How to count the total number of reflexive relations? So if there are 3 elements, then the total number of reflexive relations will be 2 to the power 3 square minus 3. That means 2 to the power 6. So for 3 elements, number of reflexive relations is equal to 2 power 6. I hope this part is clear to everyone. Now coming to the next part, that is the symmetric relation. So R is a relation defined on the set A which is not equal to phi. So R is the relation on the set A, that means R is the subset of A cross A. So R is called symmetric relation if if A comma B belongs to the R implies B comma A is also belongs to R. Okay, so if your R contains the order pair AB, then its reverse order B comma A, these element will be in the set R. Okay, so take example. Suppose we have one set A, it is 1 2 3. Now I am going to define a relation R1 which contains the order pair 1 comma 2, then 2 comma 3, and then 2 comma 1. My question is this relation is the symmetric relation? Answer is no, because 1 comma 2 present, so similarly 2 comma 1 is also present, but 2 3 present, 3 2 is not present. So it is not a symmetric relation as 3 comma 2 does not belongs to the set R. Now question is, if I am taking these sets 1 comma 1, then 1 comma 2, and then 2 comma 1, the question is this a symmetric relation? Answer is 1, because 1 comma 1, if you interchange, the same element will be present. So in the set theory, repetition of the element is not required, is not acceptable. And 1 2 is the element of R2. Similarly, just reciprocal of it, change the order, it will be 2 comma 1 is the element of R2. So this is the reflexive relation. Now the question is how many reflexive relations we can define if on a set which has a n elements. So for example, suppose if we have here n elements 1 2 3 like dot 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 n, and here also 1 2 3. So on A cross n, A cross A, we have total how many elements in A cross A? So A cross A contains total n square elements. So now for the symmetric relations, so there are how many diagonal elements? For this matrix, the number of diagonal elements is n. Okay, now for these n elements, there are how many choices? For each element, there are two choices. If you take 1 comma 1, it will be symmetric. If you don't take, still it will be the symmetric. If I put here R3, so now still 1 comma 2 and 2 comma 1 is present, then it is a symmetric relations. So for every 1 comma 1, 2 comma 2, 3 comma 3, either you will select or you will reject, still your relations will be the symmetric. So for there are how many choices are there? So for every element I have two choices. For every element I have two choices. So there are total n elements in the diagonal. So this is for the diagonal elements, I have the choices. Now what about the non-diagonal elements? The total number of elements here in this matrix is n square. Diagonal elements minus n. So it is the off diagonal elements. So in off diagonal elements, half of the elements is lying above the diagonal, half of the elements lies below the diagonal. Okay, now for every elements above the diagonals, if you are consider, for every elements you have only what? For suppose this element, if you are taking 1 comma 2, so if you take 1 comma 2, automatically 2 comma 1 will be selected for the symmetric relations. So we will focus only the half part of the matrices. So in how many ways we can select these half of the elements of these matrices except these diagonal elements. So that much choices will give the selection of the off diagonal elements for the symmetric relation. If I choose 1 comma 2, 2 comma 1 automatically will be selected. If I choose 2 comma 5, then 5 comma 2 will be automatically selected. So therefore for the off diagonal elements, we have how many choices? For each element I have two choices. So n square minus n by 2. So therefore it is 2 power n and it is 2 power n square minus n by 2. So when you simplify, the power will be n plus n square minus n by 2. That means it is 2n n square minus n. So what we have, n square plus n by 2. The total number of symmetric relations will be 2 to the power n square plus n by 2. These are the total number of symmetric relations on the set A, where A contains the n elements. Okay, now so take one example of symmetric relation. Acha, before doing the antisymmetric, take one example for the symmetric relation. Suppose A set contains 4 elements. There are 4 elements, 1, 4, 5 and 8. The question is how many symmetric relations I can define. How many symmetric relations I can define here. Okay, now how many symmetric relations? So according to this formula, we have 2 to the power n square plus n by 2. So number of symmetric relation will be 2 power n square plus n whole divided by 2. So that means we have 2 power n square is what? 1, 2, 3, 4. So that is 4 square plus 4 by 2. So 4 square is 16, 16 plus 4, 20, 20 by 2. That is 2 power 10. That means 1024. So 1024 symmetric relations we can define on the set A, which contains the 4 elements 1, 4, 5 and 8. Okay. Now coming to the antisymmetric relations. What is antisymmetric relations? If R is a relation on A which is non-empty, then R is called antisymmetric. Antisymmetric if A comma B belongs to R and B comma A belongs to R, implies, so if these two belongs to R, implies A is equal to B. This is the definition of antisymmetric relation. So R is a set in which this type of order pair presents. So if AB and BA present, it is only possible when A equal to B. So take one example of antisymmetric or non-antisymmetric. Let R is the relation which contains 1 comma 2 and 3 comma 4 suppose, and at the same time it contains 4 comma 3. So my question is, this one is antisymmetric or not? So you notice that this type of element present, AB and BA. AB present, at the same time BA present. Okay, now so AB BA present, but you notice that 3 and 4 are not equal. So it is not a antisymmetric. Not antisymmetric. Clear? So AB and BA, if both present at the same time, they must be equal. So this is not the antisymmetric. Take another example, call it is R1. R1 is a relation set of all AB such that A divides B and B divides A, where A comma B belongs to natural number. So A divides B and B divides A, it is only possible when both are same. So it is a anti-symmetric relation. Then it is possible because you are choosing the element from the set of natural number. So if 2 divides 4, at the same time 4 cannot divide 2 unless until both are the same elements. Okay now. One more important thing about the anti-symmetric relations. So in anti-symmetric relation, what we notice that if AB belongs to R and BA belongs to R, then A equal to B, then it is anti-symmetric. But if the half part is complete, that means if you show that AB belongs to R but BA cannot belongs to R, AB belongs to R but this part is not true, this cannot be happened for this set, then what will happen? It is automatically the anti-symmetric because it does not satisfy the condition for symmetric relations. So take one example of it. Suppose I am saying that R is a relation set of all x comma y, where I am taking x and y from the set of natural number. My target is x is greater than y. So by default, what you notice that if x is greater than y, that means this number is bigger than this one. At the same time, this number can never be bigger than the x. So if xy belongs to natural number, x greater than y, it implies that y cannot be greater than x. So therefore this part is not fulfilled. Only this part is belongs to R. So this will implies that R is anti-symmetric. R is anti-symmetric. Only first part belonging to the set, second part is impossible, second order pair y comma x is impossible to belong to the set, then it is the anti-symmetric relations. Okay now. Okay, before starting the transitive relations, now I am going to ask you one question. Suppose a set has n elements and here the number of symmetric relation is equal to the number of reflexive relation. If it is happened and your set, I am saying the A is not equal to 5, non-empty set, matlab A must contains some elements. Now the question is, what is the value of n? What is the value of n? We know that number of symmetric function, how to calculate 2 to the power n square plus n by 2. This is the total number of symmetric relation defined on A. And number of reflexive relation has the 2 to the power n square minus n. If both are equal, bases are same, so therefore power should be equal. So n square plus n is equal to 2 times of n square minus n. Now n square plus n is equal to 2n square minus 2n. Next what we have, take this element on the right hand side, everything. So it will be 3, I think n. Not 3, 2n square minus n square, it is n square, minus 2n minus n, it is 3n, which is equal to 0. Now n is the number of element in the set A. So what we observe that n cannot be 0, this part is not true, so n must be 3. So what we observe that if a set has 3 elements, then in that set, if you define the relation, so what we have, the number of symmetric relations and the total number of symmetric, total number of reflexive relation are the same. Okay, now total number of symmetric and total number of reflexive relations are same. Okay, now coming to the transitive relations. What does it actually mean? If you define a relation on the set A which is not equal to 5, then if A comma B belongs to the R relation and at the same time and this one, okay, and B comma C belongs to R relation, then it will imply A comma C belongs to R. Then it is the transitive relation. Both the order pair belonging to R, then the third order pair must be in the R. If it is happened, then it is the transitive relations. So now take one example. Suppose I have a set A which contains 1, 2, 3. I am defining a relation R which contains 1, 1, 1, 2, then 2, 3, and then we have 3, 1. Now the question is it transitive? So look, 1, 1 present. If 1, 2 present, so this is my A, this is B, this is B, this is C. So 1, 3 should present in the set, but here 3, 1 present, 1, 3 is not present. So since 1, 3 is not belonging to R, so we say that this R is not transitive. These R is not transitive. Okay, now if I take R1, which is equal to set of all 1, 1, 1, 2, then 2, 3, and then I have 1, 3. Now the question is it transitive? So 1, 1 present, 1, 2 present, 2, 3 present, so 1, 3 is also present in the set. Now you have to check all the possible combinations of A, B, B, C and C. So 1, 3, 3, 1 is not present, 2, 3, 3 not starting from 3. Now 1, 2 is starting from 2, only 1. So this one is the reflexive relations. Now consider one more example. Suppose X, we defined a relation in such a way such that R is a relation which contains all order pairs XY such that X is a wife of Y. Now the question is the relation transitive relation? So if X is a wife of Y, if you consider this order pair XY belonging to R, that means this one is female and this one is male. So if XY belongs to R, naturally this male cannot become the again female. So therefore the next part BC cannot belonging to this R. So therefore we cannot show that it is not a transitive. The condition of not a transitive is AB BC belongs to R but AC not belongs to R. In all other cases it is transitive. So since XY belongs to R but Y comma Z is not belonging to R, it will implies that R is transitive. R is transitive. Hope this part is clear to all of you. Next part is equivalence relations. So now we will discuss in the next lecture about the equivalence relations. Bye. Have a nice day.